This is my first year at PASS, and I'm actually truly enjoying it and learning and getting to know some really fun people. My name is Natasha Balac, and my background is in machine learning. I have a PhD in machine learning on mobile robots, actually autonomous mobile robots before that was a real thing. We were just making it up in academia. And about 5 years ago, I started my own consulting and called Data Insight Discover. I'm still at UCSD teaching, doing some research. And I'm a director of Interdisciplinary Center for Data Science. And I do teach a lot of big data, machine learning, AI courses. As a matter of fact, I taught one on Monday. We had an all-day workshop on data science in a day, and I see a couple of familiar faces here that came from more torture, so thank you for coming back. So today, though, we're not going to talk about the entire life cycle, although I will kind of mention what the life cycle looks like. But today, we're going to focus on the data preparation and cleaning. And mostly because data preparation and cleaning takes the majority of the time of a data scientist, and I'm sure you've heard these numbers anywhere. We used to say 60% of the time of the entire data science lifecycle is spent on data preparation and cleaning. Those numbers have grown to 80 and even 90% of the time. So it really depends who you ask, and I'm sure people will argue with you about it. I actually have some numbers from the studies to show you what has been reported in industry. It's really squeaky down there. So we'll talk a little bit about that life cycle of data science and the CRISP-DM standard. Then we'll talk about, as you go through each one of these stages, we'll spend a little bit of time on data understanding and then spend probably 90% of the time of this session on data preparation and cleaning, which will entail data integration, pre-processing, cleaning, performing data transformation, then feature selection and feature reduction, or dimensionality reduction as we call it. And then we'll talk about how do we find outliers, anomalies, and what can we do in terms of data prep and cleaning by utilizing a lot of interesting visualization tools. So that's what we're going to spend the next hour and 15 minutes on. Are there any questions before we start? Anything? I'd like this to be kind of an open forum. I do have a lot to talk about, but happy to answer questions during or after. So before we get going, I kind of wanted to talk a little bit about what data mining is. And you might notice that I've mentioned data science, machine learning, data mining already, predictive analytics probably somewhere in there, so I will clear up with the terminology in just a minute. But the idea behind all of these new, what we call new technologies, which are really an adaptation of a lot of existing machine learning algorithms that have been in existence for 20 even more years, is the idea that we can take a set of technologies, sift through the data, and find some unexpected relationships from large volumes of data, because human eyes and brains don't really work very well on such large amounts of data with large complexity, and we can, as humans, find those patterns ourselves. And so just like you all heard about big data, and big data is kind of a terrible term for what it really represents in my mind, data mining isn't a great term either. If we're going gold mining, we say we're gold mining because we're looking for gold. Data mining would imply we're looking for data. Well, we have more data than we know what to do with. We're really looking for patterns, insights, patterns, maybe anomalies. So we are really looking for these implicit, previously unknown, unexpected, potentially useful information. So everybody has probably heard about diapers and beers by now, or how Walmart has done analysis of data before one of the hurricanes in Louisiana and discovered that besides the bottled water and canned foods, people were buying Pop-Tarts. Well, that was comfort food, and it could stay for a long time, even if you don't have electricity. They taste better warmed up, but you can eat them cold, and they're still pretty tasty. So a lot of these kinds of patterns can be found by utilizing what we call data mining techniques, and it's really a mix of statistics, AI, some database technology, what we used to call pattern recognition in the old times, and being able to get through that data and be able to find some interesting knowledge. So if you think about what a typical workflow of data mining looks like, we collect a lot of historical data. People used to ask me, how much data do I need to collect to have enough large size sample? We used to say 2 years, but now really the products are changing so quickly. The behaviors could possibly change so quickly. New products are coming online. 2 years might be stale, might be too old. If you have sensor data and the data is coming to a millisecond, you probably don't want to use 2 years of data. So all of my students from Monday know if you ever ask me any question, I will say, it depends. So it really depends on the product or project you're trying to work on. Yes? So yes, you're right. So more data maybe is better data, but for different purposes, right? For machine learning purpose, and if you're trying to just find patterns and trends that happen over a long period of time and how they have changed, sure, you can use the data since 2005. But if you're trying to predict your customer behaviors on a specific product, and that product has only been, in production or in sales or whatever your product might be for a year, then, well, you're probably just going to work with that year's worth of data. But that's a great question. There's a lot of arguments about that in the industry and actually in academia too. So what we want to do is explore that data, then clean it, and then we create what we call a training data set. That training data set is going to help us train that machine learning model. And the machine learning models learn from experience, from seeing more data, they become more accurate and they make better predictions. So once we do create that predictive model, and we'll talk about, there might be more than one predictive model that we create, but let's say for now, for the sake of this conversation, we just create one predictive model. Then we're going to utilize some additional data set. A test data should never be seen by the model during the training phase. So it's the data that the model has never seen before, but it's of a similar kind of data. And we use that test data to test our model, to evaluate and validate the model, to ensure its quality, predictive power. And then we can put that model into production, deploy it, and the new data will be coming in. We're now making predictions and utilizing this model. This process is called scoring, and it's kind of an old term. While we perform these predictions, originally when some of these machine learning algorithms started being applied to industry, they were mostly being applied to scoring the customers in terms of accepting the next offer, coupon, or the annoying junk mail that you get. So many different types of machine learning algorithms and methods. We talk about 3 general categories of machine learning models, which are supervised, unsupervised, and reinforcement learning. And the supervised algorithms are typically the algorithms where we consider classification or regression, where we have an outcome, specific outcome or specific variable that we're interested in predicting. Is this customer going to buy a product? Is this customer going to churn? You can imagine that as one column in your Excel spreadsheet, for example. And those algorithms can predict categories or numeric values, and those are your typical classification types of algorithms. We call them supervised because we're supervising them like a teacher would supervise a child, telling to the model, there's this one column I want you to predict. The other grouping or the other category of these algorithms are called unsupervised, where we just give it all the data and we let the algorithm find some structure. So a good example is clustering or customer segmentation, where you find groupings of customers that are similar to each other, or finding those rules like diapers and beers and other types of algorithm, but you're not supervising the algorithm at all because you don't have that one specific column or outcome you're predicting, which we call class variable. So it's called unsupervised. The third category is called reinforcement learning, and the reinforcement learning is typically applied to mobile robots, to the theory of gaming, to, for example, Kasparov playing chess against the Big Blue. There was a lot of reinforcement learning there to improve the algorithm as it was playing the game further. But you don't see reinforcement learning used in traditional machine learning applications so much anymore. Yes?
With unsupervised, is there still a training and testing phase?
Correct. Both have training and testing phase. It's just in one of them you have a column you're trying to predict, and we call that labeled data. which means that you need to have from the historical data enough of that labeled data of that column collected in order to learn. And then the scoring will provide the category or the number that you're predicting in the classification, or in clustering, the scoring is which cluster does this customer belong to, right? So it's very different in the way you evaluate the models, but the process is still the same. Good question, thank you. So the terminology. So a large body of knowledge from the computer science is called artificial intelligence, and it's really started with the idea that we can give computers the ability to think like human, that they can sense and adapt, that they have this cognitive power. Still haven't quite reached that, but we're making strides in that direction. Some subset of the algorithms from the body of knowledge of AI were algorithms that were called machine learning because they had the ability to learn from experience, algorithms whose performance could improve as we give it more data. And those algorithms suddenly started being applied to all kinds of problems, and actually one of the early problems that they applied it to was stock market prediction, right? And they started performing really well, so they became adopted by industry. And at the time, the AI was not popular at all. If you think back to 60s and 70s, AI was not a cool thing. People were talking about, robots taking over the world, people losing jobs. We're still talking about that, but that's okay, because these algorithms actually showed some pretty clear, large ROIs and started getting adopted. The tools were starting to come out. If you think about kind of the history of machine learning tools, we had SPSS and SAS. Those were kind of the two large sets of tools that provided these machine learning algorithms built in so you could actually utilize them. And they call these tools data mining. And I already expressed my disliking of the word, but that's what it was called. About 8 years later, analytics tools came around. OLAP came around, and these business intelligence tools, analytics tools, started being integrated with a lot of these COTS, and it was probably marketers that came up with the idea that, okay, now we have data mining, and then we have an analytics, and what's the difference? There was actually a lot of confusion. Do these tools do analytics or predictive analytics or OLAP or BI? And so they said, okay, now we have analytics tools, and now we're going to have predictive analytics tools. To be completely honest, data mining and predictive analytics is called interchangeably, and people kind of just assume it's the same thing. For many years, there was a big argument about whether neural networks belong to machine learning or they're truly an AI set of methods. Everybody kind of gave up on that in recent years, and especially with the onset of deep learning, they're still called machine learning. Then big data came around. With the onset of big data, people who were building these predictive models were now suddenly needing to understand parallel, distributed architectures, large-scale data movement and processing, and this is when we started having those unicorns, because nobody could find a good data scientist that can do everything, write equations, understand marketing, build predictive models, be able to do parallel and distributed processing in Hadoop and HDFS, eventually Spark. So the term of data science really kind of marries the building of predictive models and these large-scale infrastructures in order to deal with this wide variety of data. So I hope that's my interpretation. No better way to present things than Venn diagrams if you're a computer scientist. So I hope that at least helps with the terminology, because a lot of people ask me what's the difference between machine learning and AI. And so I hope that kind of helps everybody understand. In 2002, with all of these SPSS, SAS, and all of these tools became kind of more adopted and more popular, all of the organizations and companies that were working on these tools came together and created the CRISP-DM, which is called Cross-Industry Standard Process for Data Mining. It's since 2002 that it hasn't been updated. However, it's really not a standard per se in terms of IEEE standards where things change all the time. It really is a process that you should follow if you want to deliver predictive models and you want to work within your organization. It kind of guides you through these phases of what you should do, where should you start. So it's more of a guide than a standard, and actually the SPSS version is a really pretty great version to read because it walks you through a little example of an online store so you can really understand what are the products that you should produce in each phase, what are the documents, who should you talk to, where should you be in terms of knowing, having, accessing the data. So today we're going to talk about these two phases. We're not going to talk about business understanding when we assume we all have a business understanding of the problem we're trying to solve and business questions we're trying to answer, but we're going to talk about data understanding and data preparation and cleaning and really focus on that area. We have spent all of the Monday talking about all of these phases and then modeling and evaluation. However, in an hour and 15 minutes, we don't have time to cover all of that. So we're going to focus on data prep and cleaning because that takes the most time. If you think about big data and data science, how it has changed this process of CRISP-DM, a little bit, but not a ton. Instead of just having a data prep and cleaning, now we have to think about where the data sources are coming. Are they coming in streams or batch? How are we going to manipulate that data? Are we doing ELT or ETL on the data? Where are we performing these computations? Is it in the cloud, on the edge, on-premise? So that whole kind of right-hand side of that data acquisition and preparation has kind of expanded, and we have to do and consider a lot more than we did just in a plain CRISP-DM. But the phase still really is there to accomplish the exact same task. Find the data, prepare, and clean it. If we go over to the left-hand side of that chart, creating that training data model still entails the same steps. You hear a lot about feature engineering. This is the more creative and fun part of the data prep and cleaning in my mind. I think this is what attracted me to machine learning, because you can be really creative and come up with all kinds of different variables. We can transform your variables that you have. We'll talk about all of this in a little bit. You can select the features. You can then start trying a bunch of different models with different parameters. You're going to kind of turn all these knobs and optimize the parameters to get the best possible machine learning model. And then you need to evaluate the models. And we talk about the holdout method for evaluation, or the standard tenfold cross-validation, which has been kind of adopted as a standard. Once we're happy with all of that, it's an iterative process. CRISP-DM is an iterative process, so is this data science lifecycle. You might create a data set and start building the models and realize that you need more granularity data. You might need to clean it better. You might need to create some additional features. You might need to go get the data from another department or purchase data. Or you might just realize that you can't answer the first business problem you came up with, and you need to maybe move on to the second one. So this iterative process is really where you're going through over and over again. Yes, data prep and cleaning takes a lot of time, but it's not like I just give you a data set and say, see you in a year, scrub it up real well, right? It's a process where you're cleaning, prepping, building, and coming back through that iterative loop. So let's talk a little bit about data understanding. The data understanding is that second phase of the CRISP-DM process, and it's an extremely important phase. So, excuse me. The data understanding really involves us as a data scientist or data engineer possibly, taking a closer look at the data that's available for our project. Sometimes there is, this is really critical in order to avoid all kinds of unexpected problems. We need to identify what data is available, what data do we need to obtain maybe even outside of our organization. We need to be able to have a plan of how we're going to integrate and access that data. You would be surprised how long that could take. And then you perform a little bit of exploratory analysis in order to verify the data quality, make sure that the data that you have is of a quality you can actually use. Now, you're not quite cleaning and prepping the data, but you are taking a deeper look into what you have at hand. And then in that process of data discovery and access, you might need to go talk to other departments. And God forbid you go and get the data from another department because they love their data, right? We've seen that many, many times. This is actually why kind of the data lakes and the whole Hadoop system has become really great, because it in some ways democratizes the access to the data. But even with that, many organizations don't have that. I can't tell you how many organizations I work with that still has Excel spreadsheets across different departments, or even across different sections of different departments, and the other part of the department doesn't even know what the other data set is, or who has it, or what state it might be in. There might be legal issues if you're working on some sensitive data. There might be legal issues of what you can or cannot obtain, and you kind of need to understand the risks of utilizing that data. There might be formatting issues. There might be connectivity issues. You might just not be able to get to the data. One of our projects, we actually had to have somebody literally deliver a hard drive to us of the data because they have so many different issues. Data was in Europe, and part of the data was not accessible, and there was all kinds of different architectures that you need to work on and different timing. Yes? I'm sorry? Yes, I will. We're getting there, yes. So in terms of the data integration, there's a lot of pieces to integrating a data. Data is typically coming across many different applications and coming in many different formats. We need to consider whether data is structured or unstructured. Do I have some structured data, and then maybe I have some tweets and some text, and I need to be able to integrate all of the data. There is no one-size-fits-all for data integration. We often have to integrate data from the third party. There's a lot of data sets that are being bought and sold out there. We might need to migrate the data from one system to another. We need to integrate the data from the warehouse and the data lake, and maybe some legacy data that is in who knows what kind of shape. So all of this needs to come together, and we need to integrate all of these components into one coherent training data set. It's much easier said than done, and we oftentimes need to integrate metadata from different sources. Let's say we have two databases, and one has the a.customer that's equal to exactly the same, which is called b.customer, c-u-s-t. We need to resolve. I'm sure none of you ever have seen any of those problems. We need to resolve all of those problems and be able to bring that data together to resolve all the conflicts and to be able to understand that data is on the same scale, that they're on the same time. We have had several projects where some of the data was in Europe and some was in the United States. We have metrics versus British units. We actually have different timestamps that were not all scheduled and synchronized at the same time. And if you're doing something like condition-based maintenance, that's very important because you need to understand that something bad has happened in the past, and you need to make sure that that's consistent across your entire training data set, or you will probably bias your machine learning algorithm. So when we do integrate the data, we need to be extremely careful about the redundant data. And for machine learning algorithms, that's even more important than maybe some other. It's always important, but it's extremely important in machine learning because a lot of machine learning algorithms expect that you have independence between your variables. And so if you have two variables that are exactly the same, they're highly correlated, as you will see later, we will take one out. Well, if we don't realize it or we don't, or as we are integrating the data, we try to avoid having to deal with that down the road. So redundant data can often be handled by correlation analysis, and that's one of the first steps we do in data prep and cleaning. And being able to do careful integration can really help avoid a lot of challenges later. We've talked about that extraction, transformation, and cleansing. So we do some cleansing through the ETL process, but in terms of machine learning, that's what we call that basic cleansing and being able to integrate the data. We are going to do additional cleansing in terms of machine learning later on in our process. If we're dealing with large data sets and we have data in data lakes or HDFS or wherever, whatever choice of the data architecture you're using, we then typically talk about ELT, where we're extracting, loading, and then maybe transforming later. I think this is probably not necessary for you guys, but there's a lot of different data integration tools, and this isn't really about just data integration, but it is an important step in data preparation, cleaning from data mining. Usually people ask me, so what are the best tools out there? This was the latest Gartner's Magic Quadrant for the integration platform as a service, and you can pick your tool. Probably majority of the tools are listed here are all pretty good, and it just depends what your organization uses, what you have expertise in, and so on. So now the data preparation is that third phase. We have learned about data we have understood where the data might be. We think we have a pretty good idea about data quality, although you really never do until you actually look at the data. And most of the projects I I can't even quote the data prep, and I've talked to many people that do similar kind of consulting because we have all gotten burned so many times. People would say, our data is clean, we have great data, we take great care of our data, and that's true, some data is dirtier than other, but I've never in my life seen clean data set, unless it was a made-up one that we used to teach machine learning, and it has 14 rows and 5 columns. So there is no such thing as clean data, and data preparation is extremely, extremely important. We really want to understand what are our descriptors, or attributes, or values, or features, or whatever you like to call them. We need to understand their ranges. We need to understand the labels. If we're thinking about doing classification algorithms, we need to have that label column, and we need to make sure that column is clean enough and representing the data well. We need to understand how data is collected. There's a lot of tools out there. There is one really good book that's written by Witten and Frank called Machine Learning something. I'll think of the full name. But they give a lot of really interesting examples. It comes with a tool called WECA, and they're from New Zealand. And they actually got funded by New Zealand Agriculture Department to create this tool for people to use in order to predict anywhere from crops to animals. And it's a great tool. It's a great book because it's really well written, and they talk about a lot of examples. And one of the examples they bring up is actually that they have done some analysis in the rental car company. And in the rental car company had a lot of data about who rents the cars, and they wanted to create some predictive algorithms. And they looked around at, times and periods and seasonality and all of this, and they found out that there was a lot of people who lived in the neighborhood that rented the cars. And they thought it was kind of strange because it didn't seem to be a type of neighborhood where people would be renting cars. So they went and talked to the people who collected the data, and they said, oh, well, when people came from another country, we couldn't put their zip codes into 5-digit zip codes, so we just put a local one. Have you ever gone to a grocery store and forgot your frequent shopper card, and the kind person, the checkout says, no problem, I'll just swipe this card, right? Messing up data mining, right? Because now you have thousands of people on one card, and it's absolutely going to confuse any machine learning algorithm ever trying to figure anything out. So history, how data was collected, who has collected, why, what was the purpose? How did they set up all these variables? Meaning and some relationships between variables is very important as well. And we really need to understand all of that just to be able to figure out whether we can answer those business questions. So let's say we collect all of that data from multiple sources. I'm pretty sure we have a lot of DBAs here. They're probably cringing because most machine learning algorithms will expect a flat file. That's not the case so much anymore. There is a number of different applications that will do machine learning directly in the databases. But when I first started doing this, I would go to the DBA and say, could you just flatten it? And they're like, I just worked on the third normal form, and now you want a flat file? Unfortunately, that's how most machine learning algorithms have been created to work. There are some optimizations done in the recent years. And then we're going to prep that data. And oftentimes people ask, so, okay, you have a test data set and a training data set. Do I do prep first, or do I only prep the training data and I leave the test data as is? What do you guys think? Kind of giving you an answer there, but we need to prep the data and then separate in the two. But then you say, okay, that's great, but then what happens when new data comes in? That one is not prepped, and I want to score it. What's going to happen? You have to prep it a little bit. So whatever you do to your data to use it in the machine learning, and I think a lot of people kind of look over that fact, is the same thing you're going to have to do as the new data comes in, right? So if I'm creating features on my training data set and they don't exist in the raw data that's going to be coming in for me to score it, I'm going to have to do that same thing on that raw data stream. So just something to keep in mind. So the algorithm input, typically we talk about attributes or variables, or in machine learning we call them features. In the old times, the features were only the attributes we actually created engineered features out of. In this day and age, people just call every attribute a feature or variable. And every single row is typically called an instance. And the attribute values are typically, as I said, assumed that they have no dependence to each other. However, if you think about if you're collecting data about the athletes for the Olympic Games, they have a height and weight. There might be some correlation between the height and weight for the athletes. Actually, we did that study with some of my students in one of my classes, and it's actually pretty interesting to see that there is much less correlation than you would think. Because you can imagine there's all different kinds of disciplines, and athletes in different kinds of disciplines might have different BMI, different height and weight, right? From the gymnasts to maybe sumo wrestlers and anything in between, right? So the other aspect of this is, and we'll talk about this, is that spouse name might depend on your marital status and the other way around. So when we think about data set, this is typically how the clean training data set should look like. I have rows, which are attributes or features. I have instances, I have columns, which are attributes or features. And I have instances, which are rows. And then whatever value each one of these attributes takes, we oftentimes call that attribute value pair. So for some of the algorithms, we will utilize these attribute value pairs, and we will kind of manipulate them in different ways. What data typically looks like is kind of this. There's a lot of missing data. There might be missing entire rows. There might be even missing entire columns. There might be constants. There might be, if this is my class variable, it's my label that I'm trying to predict. It might be completely inconsistent. Yes?
So usually the standard percentage for training data versus test data, like 80% of...
So yeah, so usually if we do a holdout method, it used to be 66-33. Then people say 70-30 or 80-20. It depends on your data set and how much data you have and how much variety you have. But that's called a holdout, right? So you'd have entire data set and you take 80% for training and 20 for testing. And that's okay to do while you're kind of building the models. But once you finish the model, you really want to do a tenfold cross-validation. And the tenfold cross-validation basically takes all the data, puts them in 10 buckets, and randomly, and stratified, which means that you have examples of those class variables. You don't want all the apples in training, all the oranges in testing, right? You want to equally separate them across. And then you'll take 9 buckets to train and the 10th one to test. And you'll write down the error of that model. And you do that 10 times, and in each iteration, a different bucket is taken out for testing and the other 9 for training. And then you average that error. And that error gives you a good estimate of how well your model will perform in the future unseen data. At the end of that process, though, this is the best of both worlds, is you take the entire data set and create the final model. So you're well evaluated and you're utilizing everything you have to create the model. So this is why tenfold cross-validation is kind of the standard. However, if you think about it, you're building 10 models and you're throwing them all away. You just really want to see what error each one of them produced so you can average the error of those 10. But you are building 10 models. So if you have a very large data set and you have a computationally intensive machine learning algorithm, that can take a little bit of time. So what you see most scientists do is do 80-20 or 70-30, keep building, optimizing, changing, and when they come to a point where they're pretty happy with the model, they'll do tenfold cross-validation. That's usually the one you see reported in papers and white papers and things like that.
Real quick, for exploratory data analysis, we are not actually changing anything. Is that true? Because the changing part will come in the data munging phase, right? Data wrangling.
Correct.
Do the feature engineering, missing values, fixing outliers, and all.
Correct. So in exploratory data analysis, you're really just exploring the data, and I'll show you in a minute what kind of that looks like. And then if you really want to change anything, that's considered data prep and cleaning. Correct. So what data should look like is something like this, right? We have a reference, we have the time, the location, the count, we flatten that data, and we really have it clean with no missing data or no noise, right? That never happens, but that's the idea. So data prep and cleaning data prep is really manipulating that data into a suitable form that we can then use as a training data set for further analysis. And so this process can take many different tasks. Sometimes you hear it called, as you mentioned, data wrangling or data munging. It's data wrestling or whatever it might be. And really, it's just taking that raw data and creating this training data set that can be valuable and useful for actually building the models. So the importance is that if garbage in, garbage out. If I put dirty data in, I can't expect the model to be really, really good, and I can't really expect a good predictive power. If I have low quality data, I might need to do some more cleaning, or I might need to go and obtain some additional data sets. Oftentimes students ask me, is there such a thing as too much cleaning? What do you guys think? It depends. Thank you. He's catching on quickly. I should start giving awards for that. Theoretically, yes, because you could input bias as a data scientist as you clean this data, right? Then you might impute too many values and cause issues. But to be completely honest, I've never seen that happen in practice because there's always so much to do that very rarely can you actually over-clean the data. You could over-clean if you had a completely empty column and you just filled it with random numbers. Yeah, that would be a problem, right? But typically you don't see that actually happening. Sometimes we think we have plenty of data, and I always like to give this example. Let's say we have 15 years of data, and we're studying election. We only really have 3 examples, right? We're studying Christmas in these 15 years. We only have 15 examples. So okay, you can say, okay, well, I can start learning about what happens 30 days before Christmas. So I have 30 days times 15. That's still not a very large data set. So oftentimes, even though we think we have an extremely large data set, we might not have enough quality data or type of data that we want to utilize to build our model. Or that class column might be missing a lot of information. We might not have a class column at all, or we're really wanting to do supervised learning. Question? I'll talk about that in just a minute. If I don't cover it, please ask again. But yeah, I'm going to talk about imputation. So a lot of people say that data scientists spend a lot of time on cleaning the data. As a matter of fact, there were some articles saying data scientists are just data janitors. Totally not true, although we do spend a lot of time cleaning the data, and I always tell my students, become best friends with your data set. Really get to know them. So some numbers are that median amount of time data analysts spend working is 4 to 6 hours a day, or 4 hours, 66% say 4 hours each day. At least 2 hours a day. So it varies, depends who you ask. Data preparation is an essential task. So there was a study done that showed that asked data analysts and data scientists, how much time do they actually spend on each one of these tasks. You can see that preparing the data and accessing the data is a huge percentage of time. And then they asked them, what tools do you use? And sadly, it's still spreadsheets and some scripting and some embedded functionalities in BI and maybe some other tools. This study was done about 2 years ago, 3 years ago almost now. So there might be some changes that have been happening in the meantime. So the data prep goals are to identify sources, consider the formats, identify how to access the data, select the features, reduce the features, engineer the features, and then being able to determine what features do we want to keep or not. So the data prep question, is the data complete? The answer will probably be no. Does it have any outliers? That's one of the first things you're probably going to want to look into it. Does it need cleaning? I'm sure yes. And do you need to fill in the missing values, keep them, or eliminate them altogether? These are all the questions that will keep coming up as you go through the data cleaning. So 2 things we already talked about. If I have classification, I need to have that class variable, that labeled data. If I'm doing unsupervised learning, maybe I'm a little less concerned about that. But I'm always concerned about 2 things when I'm building machine learning models. And when I'm cleaning the data for building machine learning models, I need to think about 2 things, overfitting and underfitting. Does anybody know what overfitting means in terms of machine learning? Yes? Correct. So when we think about building machine learning models, we're trying to generalize on the data we're learning from. So if we do overfit that model to that training data set and we learn every tiny intricacy about that data set, we're not generalizing well enough and we won't perform well on the future unseen data. So there is a fine balance between learning too well and not learning enough on that training data. So if we talk about overfitting, that means that we really want to have that good predictive power, but it comes from the generalization of the data we have learned, and we don't want to, and oftentimes you'll have conflicting data in your training data set, so you really need to, your machine learning algorithms need to be able to resolve that. Underfitting just means there might not be any patterns in data, and that sometimes happens. Even if you do the best job cleaning, they just might not be the patterns that you thought they would be there, and your experiment might just flop. But the good thing about this is that once you start and you list all of your business requirements, what you will end up doing is, which is actually kind of the fun and the difficult part of this process, is you're always going to say, oh, I just found this, I'm going to go explore this. I'm like, no, stay on this path, right? This is why documentation is great. But there's always so many different directions, and you will find some little interesting nuggets of knowledge as you go through that you can answer a lot more questions than you start with. So being able to just kind of stay on that path is important. But that can happen, and underfitting, it can become an issue. So here are the steps of the data processing and cleaning. First, you consolidate the data. Then you clean. First, you're going to remove inconsistencies, reduce noise, look into outliers, and decide what to do with missing data. Then we're going to transform the data. Sometimes we need to aggregate. We need to discretize or normalize the data. And then we want to perform some feature engineering. Once we do that, which sounds kind of silly, I just added all these features. Now I'm going to decide which ones not to use. Well, you want to create as many features as you can to help that algorithm learn better. But at the end of the day, you do want to downsize and down select only to the ones that are truly impactful and truly creating the most predictive model. So we're going to walk through each one of these steps in details. So the pre-processing and cleaning, we usually start with what we call a data audit. And the data audit allows us to understand the quality ingredients that will make the predictive model. What does that data look like? What are the extremes of it? Is there any outliers? Then we're going to format the data, cleanse, fill in the, or not fill in the missing values, look at the noise and decide how to deal with the noise, then create some descriptive statistics, and then we'll talk about normalizing, discretizing, and engineering. So here's an example from a data audit. This tool is called NIME, and we actually use that tool. It's open source, although some pieces now they're becoming a vendor, but the tool is mostly still open source. And the beauty of this tool is that I can create this one little node. It doesn't require any programming, and I can just create the data audit automatically. And what the data audit is telling me really is the min, the max, the mean of each one of the values, standard deviation, skewness, kurtosis. It will show me the actual distribution of the data. So even just visually, you can use this in R or Python and create this for each one of your variables or any tool of your choice. But really what I'm looking for is these kinds of things. I want to understand, and this was actually done on a data set called adult.csv, which is a subset of a census data that we use to illustrate how a lot of machine learning algorithms work. You can find all of these data sets at the UCI machine learning repository. And so what I really wanted to do is understand what is the median value of the people in my census, subset of census data. It looks like they're about 38 years old. However, there might be an interesting point. I have somebody who's 90 years old and is possibly still working, which is interesting. I can see kind of the distribution of all the people that are working. This is an interesting point right here, right? This is the education as represented of number of years a person has spent in education. So I can see that the majority values are right over here, but I have this one extreme value right there. That might be an outlier, right? I can visually just spot that and quickly look into all of these distributions and understand a little bit more about my data. So some of the data formats that I have seen in the past, and I'm sure you guys have seen more, is date and time. How many different ways have you seen date and time represented, right? Some people go to month, date. Some people put slashes. Some people like to go down to the minute of the time of the day or the second, and maybe the other data set I'm trying to integrate with doesn't have that. How many ways can you represent first name, middle name, last name, right? How many different ways can you name those columns? This is all part of formatting that we need to deal with as we're trying to create this training data set. World currency symbols. I think I have probably seen 10 different ways to represent dollar sign. State and country. I come from San Diego, California, and you can't imagine how many different ways I've seen California spelled. Cal, CA, California. Zip codes, right? The zip codes can be represented in many different ways. We have a standard in the United States for zip codes, but as I mentioned earlier, there's a lot of different zip codes and different ways representing zip codes in other countries and other regions. We have a very wide range of values that can then be represented in many different ways as well. So we need to somehow consolidate all of that. And during this data preparation, we want to understand these variables. We want to understand their distributions. A lot of machine learning algorithms really like to have normal distribution of the variables for each attribute. It doesn't always happen, but it is something that we will look into and see if there is anything we can do to possibly change these distributions. We are going to explore the characteristics of each one of our attributes. We want to understand the min and the max and the range. We want to understand, is there a lot of missing values? How many times have you seen missing values being represented as nothing, or NA, or 0, or a question mark, or a slash, or a dash, or right? So we need to understand if that really means a missing value, or is there actual meaning to that particular character? Because if there is a meaning, that becomes a categorical type of variable that the machine learning will consider as a particular type of an outcome. If it is missing, then we need to treat it as a missing value, and we need to perform some tasks on there. We need to understand whether this is maybe a primary key or identifier that just keeps going and growing. And the beautiful thing about machine learning is that we don't really want identifiers in the data. Remember, machine learning is learning generalized patterns on the underlying data. So there's a lot of talk about privacy and ethics, and those are very serious issues in machine learning. But the nice thing about, and there is some algorithms called privacy-preserving algorithms that are coming out of research now, which is great. But when we're building the models, we really don't want any identifiers. We want generalized patterns from the data, and if we put perfect identifiers for each one of our rows in the data, we're actually probably going to skew the learning model. So while we are performing these, cleaning the training data set, most of the time you're not going to have a whole lot of personally identifying data unless you're looking at addresses of your customers, and those can sometimes identify a person. Other than that, we don't want names, we don't want primary keys from the database or anything like that. The problem is when we create that predictive model and the new person comes in and we score it against that model, then we can send, if we're target, we can send a coupon to a family and that had no idea that their teenage daughter was pregnant. And they didn't do that on purpose, right? That was just a way the machine learning model was so good that he scored it perfectly well based on all of the purchasing patterns that were happening in the past. And this is really where the privacy and ethics really comes in. But as we are creating this training data set, we typically actually exclude most of the personal information. We will probably have some noise in data. And the noise in data can come from many different sources. We need to understand and detect those suspicious values, whether they're rows or columns. We typically remove outliers, and for a long time, that was a big discussion within machine learning. Do we remove the outliers, do we keep them in? Because if the outliers are somewhat reoccurring types of values, then we should probably learn from them. If we're looking for anomaly detection, we're definitely keeping them in. If we do have noise, we might want to smooth the noise if we know that it's truly noise. And we can smooth that by looking at the neighbors, but then we need to decide how many neighbors do we want to look at. And then we can smooth it by looking at fitting the data with the other similar methods. So noise can come from many different sources. We can come from faulty data collection. It can come from data entry points. I usually have my students work on this thyroid data set, and there is a 94-year-old male that's pregnant in the data set. And there is a 145-year-old person in the data set. So probably, and this is actual data collected from a clinic, so probably it was data entry errors. But then what do you do with that? Is the 145-year-old 14-year-old or 45-year-old? How do you know? Do you fix it? Do you take it out? Do you leave it, right? And so the problem with this type of data is that if you have, for example, a thyroid data set, you have a lot of healthy people and a small number of sick people. So if the 145-year-old is a sick person and you have a much smaller amount of that data, you might go out of your way to try and figure out what happened there and try and fix it in some way. If it's coming from a large population of healthy people, you might just take it out and say, I don't really need them. So there is a lot of different reasons why we might have noise in data. It could be technology limitations. If you're collecting data from sensors, it could be that the sensor malfunctioned. Other types of noise is duplicate records, and we talked about we really try to avoid having to do that at this point of time in our data prep. We're really hoping that during the integration we can resolve some of those, but there'll still be some incomplete data and inconsistent data. So here is kind of 4 main ways that we try to deal with noise in data. One is what we call a binning method. We can sort data and we can partition data into typically equal width bins. And then we can smooth each one of the bins by the mean, or we can smooth by the boundaries, or we can come up with a way to smooth each one of the bins. And that way we kind of avoid those sharp peaks and valleys. Another way is to use clustering. And clustering, you would say, isn't that an unsupervised machine learning technique? It is. But the beauty of clustering is that we can use it as an actual predictive model, and we can use it to actually help us clean and fill in the data values. So if we're thinking about outliers, oftentimes there will be a cluster of outliers, or there might be a couple of clusters on only few values that didn't quite fit the other clusters or the data that ended up in the other clusters. So we can use clustering to detect the outliers and or possibly fill in the missing values. We can certainly use human inspection, but if the data size and complexity grows, that becomes a lot harder to do. We can use regression. There's many different regression methods that can help us fit the data into a regression function and then use that for smoothing the errors. So I have mentioned binning, and binning method is used for both for avoiding, to try and deal with noise, but you will see later we're going to use it for discretization too. So I'd like to kind of present the 2 types of binning, and those are two ways that we typically utilize for our data. One is equal width, and the one is equal depth. So equal width says, let's say we had a range of customers that were going from 0 to 30, and we wanted to discretize that data and put them in a bins. If we're considering equal width bins, we're going to have a bin that goes from 0 to 10, from 10 to 20, and 20 to 30, and so on. So they're equal width. But let's say we have 1 or 2 customers that are in the age group from 0 to 10, and then we have 1,000 customers that, that fall into the 10 to 20. Now, these bins will have very different frequencies, and that might not work well for some of our machine learning algorithms. So we can consider what's called equal depth frequency, where the width is different, but then we have roughly the same number of representation of our data in each one of the bins. Make sense? Yeah? Okay. So the equal depth is good data scaling, and it helps us with categorical values. The equal width oftentimes is more intuitive and can work really well if your data is equally distributed. However, that doesn't happen very often. And in this case, the outliers can then dominate the bins, and the data could be skewed. So something to look into your data before you decide which one of the binning methods to apply. Missing data. If we have missing data, there could be many different reasons for data being missing from the data set. Maybe customer income in sales data was not easy to obtain, so some people gave us their income and some people didn't. Maybe there was a sensor malfunction. Maybe there was data there, but somebody deleted it by accident or on purpose because they didn't think it was useful. And maybe there was data entry points, and maybe a nurse just didn't have enough time to enter all of the information about the patients. The next patient came around, and she never got around to go back and fill it in. So there could be many different ways for missing data. However, missing data can become a real problem if we're prepping the data from the machine learning, and we really have to address the missing data. So one way is just ignore it. Ignore the entire row. Usually we consider that if the label is missing or the high percentage of information in that row or the column is missing, and it's just really not going to bring any value to the predictive algorithm. We might decide to fill in the missing values manually. It's depending on how large your data set and how many missing values. That could be very, very difficult and time consuming. We might decide to just come up with the constant and just fill it in for the entire row of missing data. Probably not the best way of doing it. We might want to use the attribute mean to fill in the missing value, but only a mean for all the values that belong to healthy people for the healthy people and sick people for the sick people. So now we're kind of, getting a smaller sample of data that we're looking at similar people, or we can use machine learning algorithms to do that for us. We can use k-nearest neighbor or naive Bayes or decision tree or other algorithms that will say, this instance looks very similar to these other instances with other very similar value, and therefore maybe this is the value you should use to fill it in. Now, it kind of seems a little, redundant. They're using machine learning model to fill in the value, and I'm going to use that same machine learning model to learn from the data. But it actually does work really well, and utilizing these more advanced techniques have actually shown to create better predictive models. The other things we need to consider is if data is missing, why is it missing? Is it missing structurally? So let's say people with high salaries don't generally like to tell you their income, or maybe women in general don't like to give out their age. Maybe it's missing completely at random and there's absolutely no correlation to any other value, or maybe it's missing structurally, or maybe it's missing at random, but if women are married, they might have a maiden name, but if they're not, they won't, right? So there might be some correlation to some other variable, but it's not consistent, and you might not know that. So understanding this is really important because you will probably consider filling in those values or deciding not to fill in those values in different ways, right? Or it might be easier to fill in the values because you know they're correlated to a particular attribute. So that's data prep, that's data cleaning, dealing with missing value and noise value. Now we want to transform. So we have cleaned it, we filled in the value, or decided to take out the missing value with the noise. We're now actually at the point where we can start thinking about transforming the data. And there's a lot of different ways why we want to transform the data. Sometimes we want to combine the attributes. And oftentimes, if you think about all the attributes that you have in your data, ratios can be more useful than the number itself. I like to bring up an example of a date of birth. Is that a really useful attribute? By itself, it's just a date, right? It's probably not telling me very much about my customer or employee or whoever I'm thinking about. What could I do with that date of birth to create it a more descriptive attribute? Current age, excellent. Or I can even take that current age and bin it into age groups. Or I can take that current age and do something, some kind of a fraction with the age and number of years working and or income, or number of years living at the location, or whether at a particular age a person is more likely to be married or not. Like, I can come up with so many different ways and so many different features I can create. We talked about smoothing to remove noise. We oftentimes want to normalize the data. And it's specifically in clustering or customer segmentation algorithms. If we think about having rows of data, and let's say each row represents your customer and some kind of purchase or behavior or something that customer has done, and you're trying to figure out the distance between those two instances in order to decide whether you're going to put them in one cluster and the other. And you're looking at that instance by checking each one of the variables and differences between the values of those variables. Let's say the first one is age, and I have a 30-year-old and a 50-year-old. Okay, so the difference is 20. And then let's say my next variable is income, and the 20-year-old has a 50K income, and the 50-year-old has $1 million income, right? Several orders of magnitude difference. So now if I'm calculating that distance is heavily weighted by that income. In order to prevent that, we say we normalize the data. And some algorithms like clustering absolutely require normalization. And the way we normalize the data in machine learning typically is we put it on the 0 to 1 scale. There's two different ways typically that you see people do that, is either by utilizing what's called the min-max normalization or the z-score normalization. But typically what we see in machine learning is that we'll take all the data and just map it onto the 0 to 1 range. And depending on the tool or the algorithm, that's usually a really beneficial way to treat your data. However, when you go back and you look at those clusters and you see that everything is from 0 to 1 and you're trying to understand each one of the clusters and maybe some descriptive statistics about that cluster, and you want to understand who are the people that ended up in that cluster, that 0 to 1 is not very descriptive, right? You might need to turn that back into the original value for just human interpretability. So then we might have out-of-range values. And the out-of-range values are simply values that are out of a population. And remember when I said when we clean the data and we prep the data and we create these features, we want the data that's coming in to score the model later on to kind of be the same. Well, what happens if we remove all the outliers and we say there is no negative values, right? All the data is in a 0 to 1 range, and suddenly a -2 comes in or 1.1 comes in. What do I do? What can we do? A couple of things. We can ignore the range that has been exceeded, and most modeling tools will have some capacity to handle the numbers outside of this normalized range of values that we just forced all of our variables into. And that could possibly affect the quality of the model. We can just ignore them and say, you're out of range, I don't know what to do with you, I'm just going to ignore you. Or we can throw an error and say, oh, this value is out of range. It can't be scored against the model. And I want somebody to look at it because it's really out of range and it could be a potential anomaly. Or we can clip out of those out of range values and say it's really closer to 0 or closer to 1 and just map it to one of those values and put it back in the range. I have seen all of those. I can't say that one is better than the other, but it depends on your application. They can all work in different ways. You just have to make sure that you can test and validate enough to confirm that you're avoiding bias by doing that. If a lot of values do start showing that kind of a behavior, then you could be introducing bias. And it might be time to retrain your model. So we mentioned a little bit the data discretization, that, for example, age might be better to be put into buckets. The one aspect of discretization is that you could actually lose a little bit of value, right? So if I'm putting the age, which is in a nice little range, or maybe I even have a normal distribution of the values of age, and now I put them in these buckets, and I build a model, and I oftentimes actually have my students do that. They'll build a model with numeric value and then discretize it, put it in the buckets, and build a model with that to compare those. Sometimes you do better, and sometimes you do worse. So you have to be really careful to do it for the right reasons, as maybe a part of feature engineering, or just because you know that certain types of age groups, you have very small representation, and you really don't want to overwhelm the algorithm with too many values. Yes?
Can I follow up to what you're talking about? So is it true that machine learning algorithms work better with numerical data? Right? If so,
Not all of them. Some of them.
so if I were to,
It depends.
So if I were to change a numerical categorical feature into numerical, like I can do that. For example, male, female, I can just do 0, 1. How about if there are multiple values possible for that particular feature? So is there a way we can?
Yes, so that's a very long question. I'll try and rephrase it. First part is it true that all machine learning algorithms work better with numerical data? Some. Actually, decision trees work better with nominal data, with categorical data, for example. But some, like neural networks or deep neural networks, will do better with numeric data, and some of them won't. Even some clustering won't even accept nominal data. It only works with numeric. Although I have to say a majority of algorithms have been adapted from one to the other, so you can work with each or both mixed. If you do have a categorical data and you have a lot of different values of that category, let's say you have color, right, and there's a lot of colors in the world, how do you turn that into a nominal value? So sometimes we will encode them and create new variables and say red, yes or no, 0 or 1. Blue, yes or no, 0 or 1. So we'll just create additional hot end encoding. If you only have 2 values, obviously that's much easier. But you have to always remember, whichever way you define that variable and you give it to the machine learning algorithm, as smart as they are in terms of learning more about your data, they're pretty dumb in how they're going to treat the values. So if you have a zip code, then you take that zip code and you tell the algorithm that's a numeric value and not a category, the algorithm will subtract, multiply, divide those zip codes. Is that really what you want to do? Probably not, right? Now, if you do have zip codes and you give it to a decision tree and you're working on a very large area of United States, for example, there is many, many zip codes, and decision trees don't like taking on categorical values that can take on too many values, right? So you might need to kind of merge them into additional groupings of cities or areas or certain larger segments where you have smaller number of attributes. So the feature engineering then, as I said, we've done one project where we were looking at fraud, waste, abuse in submitting medical claims. And we were looking at people going to the doctors, and we have a person's information and where they went to the doctor. Well, there wasn't a whole lot of features to work with. So we then looked into creating some new features. For example, we can create a variable to say, is this a first-time customer or first-time patient? We can look into creating a feature that says, is this a repeat customer? How often does this customer come? We can look into whether this customer lives 25 miles or whatever number we find from the data is kind of that optimal number away from this doctor or this store or this provider. And then we can look into what's the time between the visits or shopping trips or whatever we're looking into. So we can create many, many, many of these types of attributes, which is called feature engineering. Now that we created all of these attributes, we want to reduce them, which seems counterintuitive, but we really want to describe the data, taking that subject matter expertise through that feature engineering to our training data set so our algorithm can learn better from it. So then once we have all of those features, we want to try and find the minimum viable subset of features that will create us the best possible model. And there is a very good number of algorithms that can help us do that. There is dimensionality reduction methods that have been kind of adopted from math and from statistics, and we can use those methods to try and reduce the features, and I'll talk about a couple of them. But there is some simple ways to do that as well. One way is to first look at that correlation. Remember I said if we have 2 attributes that are highly correlated, we probably want to take one out and throw it out because most machine learning algorithms don't want variables that are one-to-one highly correlated. So oftentimes you'll see these kinds of charts where it will show you whether the attributes are highly correlated. If they are, then we are going to remove one of them. There is a number of different heuristics methods that we can utilize to select the features. And then there is, again, machine learning algorithms that will do that for us. Random forests are well known for ranking the features and being able to tell us which features influence the outcome of that model. And we can utilize these algorithms to rank the features, cut them off at a certain point of time, and decide which ones really are important. There's heuristics methods which say I can take all of the features I have and build a model, and then I can take one out and build a model and see if I get better or worse performance, and I just keep doing that one at a time. Obviously, that could potentially be pretty computationally expensive, and there are some heuristics and ways that these algorithms can do this in a smarter way. So we can do a couple of things that can help us reduce the number of features before we even get to any of these more advanced feature selection algorithms. One is if the entire column has a very high percentage of missing values or is all constant, we can probably remove it. If there is rows that have examined similar kind of behaviors, we can remove them. We can improve the model by understanding and adopting those new features we have created and then running those through some of these machine learning algorithms to rank the features and help us determine which features to keep. Some of the other dimensionality algorithms that we have is the feature selection or subset selection algorithms. And then there is different versions of those algorithms. One of them is called stepwise forward selection or the backward selection. One is start with 1 or 2 attributes, keep adding, and the other one is start with everything and keep taking attributes out. Decision tree will only take attributes that contribute to creating the most accurate prediction with the shortest possible tree. Sometimes people use to build a decision tree, see which attributes show up in the tree and only use those, and then maybe use a different algorithm to actually do final prediction. And then random forest ranking is a really great way of doing it. And if you have heard of PCA, a PCA is another way of creating a subset of features where we take, for given n vectors of the data in a k-dimensional space, we can take those vectors and transform them in a different space where they all are in the, excuse me, they're all mapped to the same dimension, and we can see which one of those vectors reduce 80% or 90% of the variance in our data. And then some people will actually use that as the features. However, other people will just say, well, tell me which attributes contributed to reducing the variance in this new dimensional space, and just take those features and then use it for selecting the most important features to use on. Many different ways, many different approaches. The last thing I want to talk about is outliers and anomalies. How do we know what an outlier is? Is it a statistical outlier because it's far from the mean? Is it a distance-based, so it's furthest from the points of each neighbor? Or should I use a deviation-based method that can tell us, it's giving us the largest error in respect to something we're measuring, right? So there's a lot of different ways to do that. And as I said, we had a project where we were looking at the fraud, waste, and abuse, and we found 2 providers that were like literally here, and everybody else was kind of here if you were to plot it as a function. And we were like, haha, we found the outliers, right? Anomalies. Well, it turns out those were actually pharmacists who had a special certification to give a certain type of heart medicine that all the other pharmacists couldn't dispense because they didn't go through the additional training. And of course, they looked like an outlier because they had the highest number of this specific type of medication. Now, if there was maybe pain medication, maybe a different story, but this was a specific heart medication for some pretty difficult heart conditions that really, even though it was an outlier, it was not an anomaly or fraud or anything like that. So how you define an outlier is very important. So we have a lot of data visualization techniques that can help us discover those outliers. We can utilize 3D visualization. We can examine relationships between the variables. We can utilize different types of correlations. One of my favorite ways is to use the box plots to just really look at the relationship between attributes, look at kind of where their extremes are, look at those mediums and the whiskers, and you can really visually very quickly and easily spot some of those outliers and understand them. 3D visualization is great, but maybe not always available. And the other ways we oftentimes utilize for data prep and cleaning is just lots of scatter plots. And really being able to understand those multivariate correlations between complex data that we typically utilize for machine learning, one of my favorite ones is the scatter plot matrix. So we can plot each variable against the other variable. We typically have obviously a 1-to-1 or high correlation on the diagonal because it's variable against itself, and that's okay. But what I love about it is that I can plot actual histograms and or scatter plots within this large correlation matrix, and I can, in one chart, understand a lot about my data. So visualizations are awesome, and they help us understand and plot the relationships between the data. They're great for understanding the data and being able to visually possibly spot some outliers, but really to get to know your data, understand their distributions and min and max, they're a great tool. Yes? Mm-hmm. So with the thing going from year to year, and is it really easy to read that, or how? Oh, it really, yeah. How does one get used? So the sunburst one, maybe? Was it the sunburst one? This one? Yeah, the sunburst. I love these because they're great in showing you correlations between categorical attributes usually, and it shows you how many times and how many instances these kinds of attributes showed up in. But that's pretty much it. That's kind of what they're really good at. They're not going to answer all of your questions, right? And I think we all have personal biases in terms of what types of visualization we like or not. As I said, this is one of my favorites. This is on the iris data, which is another data we use a lot to teach. But you can see I had 3 types of irises. I can clearly see the class separations here under different values of different characteristics of these irises, and I can even visually spot these separations of these classes. Now, it's just a small data set, but that actually is very useful and can help even on a larger data set. So what you guys learned today is how to select the data, pre-process the data, and transform the data. And we talked about during the pre-processing, we need to worry about the formatting, cleaning, dealing with missing and noisy values, and then being able to understand the distributions and correlations between our data. Then we talked about scaling and normalizing the data, feature engineering, creating those cool new features that can hopefully help the algorithm learn better, aggregating the data, and visualizing the data. So really, this is data prep and cleaning in an hour. It's a key issue in data science and data mining. It's an extremely important task. There's many techniques that can be used, and people say it's partially science and partially art, but it really depends on having that deep understanding and knowledge about the data. This is where talking to subject matter expert is invaluable and extremely important. So thank you. Please do the evaluations. I have made my slides available. It should be on the website. There is a bunch of really cool tools. There is a full book written just on data mining, preparation for data mining. And then there is the tidy paper that was actually used to create the tidyverse and the tidy functionalities in R and Python. And they kind of follow all the steps that I have explained and talked about today. So if you have any questions, feel free to email me, and I'll be happy to, or connect to me on LinkedIn. And if there are any questions, I'll stay around and answer. But I think we're right on time, 3 minutes late, but close enough. So thank you.